All right, welcome back. Before we get started, regarding Wednesday, which is a buffer lecture for Friday, I got the vote, and thank you very much for filling that up. So 46 of you voted that lecture 14 and 15 are the most confusing. So those are the thermodynamic relations, Maxwell relations, and using the thermodynamic relations to calculate, say, delta G, delta H, delta S, and delta A. So on Wednesday, I'll go over those topics with you along with practice problems. And then about 40% voted for chemical potential. So we'll also do one practice problem on chemical potential, likely a true and false, just to clarify the concept behind chemical potential. And also on Wednesday, hopefully I'll start with a 10-minute quick summary on all the topics we discussed after midterm 1 all the way until today, and see how these concepts are interconnected with each other and why are we doing all these math. Okay, so that's the Wednesday buffer lecture. So today we will be talking about our conventional entropy and the third law of thermodynamics. So this goes back to our appendix table, right? So in our appendix table, remember in our last lecture, we spent lots of time talking about what is the heat of formation of a substance. How is the heat of formation is being measured experimentally, and how to use this table. We also went over the CPM, the standard isobaric molar heat capacity, and how to use the standard molar heat capacity to solve for the delta H naught at a different temperature, or that's the temperature dependence of the heat of the reaction. Also, what else do we have in the table? We have delta G and S naught M, right? So in here, delta G naught is eventually, gives free energy that we want. It's related to reaction equilibrium that we will discuss in the next lecture. But today, we'll focus on our molar conventional entropy, or this term here, S naught M. All right, so today we'll first go over what is molar standard conventional entropy, how is it defined, how is it related to the third law of thermodynamics, and then later on we'll go over examples to show that how scientists actually measure the standard conventional molar entropy experimentally through one very comprehensive example together. So that's the goal of our today's lecture. Okay, so back to our notes. Originally, I was hoping to finish the standard Gibbs energy of reaction, but I don't think so. So for your midterm exam, we'll end at 5.7, just so you know. Okay, getting started. Conventional entropy. So when we're talking about conventional entropy, as a quick review, in what do we know? Right, so in our previous sections, we spent lots of time talking about how to calculate change of entropy. So this is going to be a review. Right, so we know that entropy as a state function is defined as ds over dq reversible over temperature. Right, so taking the integration on both ends, we have the integral of ds, the integral of 1 over t dq ReV. Right, so there are two different types of calculation we can do from here. So the first one is thinking about standard state or standard pressure. So P naught equals to 1 bar. And then we have our dqp equals to delta H, which, actually the integral of dqp. And that gives you the integral of Cp dt. All right, or the other way to put it, if we're having a standard pressure or constant pressure temperature change, we can calculate our delta S to be the integral of my Cp over T dt, This is the isobaric temperature change. All right. Note that we didn't specify whether it's reversible or irreversible. Remember, in our calculation, since entropy is a state function, as long as you can build or you can imagine a reversible pathway for that isobaric temperature change to take place, we can use this equation to calculate delta S. Secondly, what about phase change? So we can also have isothermal phase change or reversible phase change. So at melting point or at boiling point, the phase change is reversible. And for that, we have delta S equals to, again, we start from this dq P over T. And since the temperature is not changing at boiling point or melting point, we can rewrite that as dqp, or just qp over T. And that qp equals to the delta H of phase change over the temperature of phase change. So these are the things we discussed before. That's how to calculate entropy change of different situations, of different processes. Right, so that's a review. We'll use it later on. But right now we're facing a problem. We have all these ways that gives us a mean to calculate what is the change of entropy, or what is delta S. The problem is we don't have a universal reference point, right? So we're always talking about the difference of entropy between one state versus the other. We want to use the third law of thermodynamics to give us a way to define, hey, this is the zero entropy. Now, that goes to our first hypothesis. So in this hypothesis, we are arbitrarily set the molar entropy for each element in its stable condensed form in state where P equals to 1 bar, temperature approaches 0 K to equal to 0. So in here, first of all, the stable condensed form. So whenever you see something like H2 solid or O2 solid, like in this class, whenever you see an element in its solid form, that you can just treat it as a stable condensed form. The actual definition is more complicated and a little bit beyond this course. Now, in this case, if we write out this expression into mathematical equations, what we end up getting, well, it's a standard molar entropy at 1 bar. It's a molar entropy, so I have subscription M, 0 K. Right, so this expression is the same as, say, when temperature is approaching 0 K, my standard molar entropy equals to 0. All right, so know what each term here is. So this little dot means that's P naught equals to 1 bar, standard state. M tells you that's the molar entropy. Or if you remember, the Sm equals to S divided by number of moles. Right, so entropy itself is extensive state function. The molar entropy is entropy divided by number of moles, and hence an intensive function. And then this temperature, that's temperature. Right, so whenever you write down an equation, know what each term means in that equation. All right, but we don't live in a world that we only deal with elemental form, right? So the next question is, what does the reaction at 0 K looks like? Or that gives us the third law of thermodynamics. So we started by looking at entropy, by looking at a review on how to calculate entropy changes. Then we have our first hypothesis that the molar entropy for each element in its stable condensed form always equal to 0. And then we're ready to use our third law of thermodynamics. So the third law of thermodynamics started from an experimental observation. So what is that experimental observation? That's saying the slope of delta G naught. So delta G naught is the Gibbs free energy of a reaction. That's something you can experimentally measure. Right? So what we find out is delta G naught versus temperature. This curve goes to 0 when temperature goes to 0. Or the other way to put it is the rate of any chemical reaction approaches 0 when temperature approaches 0. Or mathematically, we can write it as when temperature approaches 0, we have the partial derivative of delta G naught over temperature at constant P equals to 0. All right, that's a mathematical expression. That's an experimental observation. You don't necessarily need to run the experiment at 0 Kelvin, but by working on rate of the reaction and, well, not the rate of the, by observing the equilibrium of the reaction, equilibrium composition of the reaction, and calculate the delta G naught of the reaction plotted against temperature, you'll get a plot that we can estimate what does T equals to 0 looks like. With this in hand, next question is, well, we have our Gibbs equation. Right, so by looking at the Gibbs equation, we see that negative S equals to partial differential of G over T at constant P. Just want to quickly remind you that in our textbook, we also say the change of Gibbs free energy is not defined if the temperature is changing. That's because it's S itself, the arbitrary value of S. That's not defined in thermodynamics. Nevertheless, so with this in hand, what do we have? We can write my delta S to be S2 minus S1, right? Final minus initial. And then using our Gibbs relation, what we have is the negative of dG2 over dt at constant pressure plus partial differential of G1 over T at constant pressure. Right, they are both differential over T, they're both at constant pressure. It's the same to say like dx plus y equals to dx plus dy. So we can rewrite this to be negative partial differential of delta G naught over T at constant P. Or what we have is using the Gibbs equation to find out that this term here, effectively that's our delta S. Or if we rewrite this experimental observation that the slope of delta G naught versus temperature goes to 0 when temperature approaches 0, what do we have? We have limit temperature goes to 0 K, and my delta S equals to 0. So far, so good. We're just starting from an experimental observation that the equilibrium of the reaction is not going anywhere, right? Delta G naught versus T is 0. We use the Gibbs equation to find out, okay, so this partial differential of delta G naught over T is effectively the same as delta S of the reaction. We find out that when temperature goes to 0, the delta S of the reaction goes to 0 or approaches 0. And then we're ready to formally state our third law of thermodynamics. It's basically saying the same thing we did. This one is the Nernst-Simons statement of the third law of thermodynamics. Like the second law, you have different kind of statement. We're just going to use this one. It says, for any isothermal process that involves only substances in internal equilibrium, the entropy change goes to 0 as T goes to 0. So this one is a little bit, it is to make it more specific. I'm not going to test you on it. The more important is this one, is the entropy change go to 0 when temperature goes to 0, or the entropy change of a typical chemical reaction goes to 0 when temperature approaches 0 K. Or the other way to put it is when temperature approaches 0, we have delta S equals to 0. That's the one we just write out. All right, so now we have two pieces of information. So thinking about what do we have? First of all, we have this one that's telling us each element in their stable condensed form has a molar entropy equals to 0 at 0K. That's first piece of information. Second piece of information, the delta S of any reaction at 0K is 0. So taking together, we can extend our previous hypothesis into the conventional molar entropy of any substance at 0K. And let's see how do we do it, right? So this part is using the two conclusions we derived before to try to get an idea about what is the conventional entropy of any substance. Now, instead of only looking at elementals like H2 and O2, we're looking at H2O solid. So what it is? First of all, let's write out an expression for the conventional entropy of this reaction, right? So delta S, it's a state function, product minus reactant. So the molar entropy of H2O minus the standard molar entropy of H2 minus 1/2 of the standard molar entropy of O2 at 1 bar 0 Kelvin. And then using our first knowledge, right, we know that these elements are in their standard condensed form. Or the other way to put it is we know that these two terms are 0. So when temperature approaches 0, my standard molar entropy of H2 equals to 0. And the same, the standard molar entropy of oxygen also equals to 0. Right. Then, using our third law of thermodynamics, we have that for this reaction, when we have elemental H2 and O2 goes to H2O, this delta S equals to 0 when temperature approaches 0. Or the other way to put it, this term is 0 due to my third law. All right. So what's our obvious conclusion here? That tells us this term here, or the standard molar conventional entropy of H2O must equal to 0. Or the other way to put it is in combination of using the third law of thermodynamics and our arbitrary assignment that any elemental form has an entropy equals to 0 when temperature approaches 0, we can generalize our conclusion that for any elements and compounds, we have the standard molar entropy goes to 0 when temperature approaches 0. Right. And since molar entropy just equals to entropy divided by number of moles, if molar entropy is 0, entropy itself must also be 0. And that's the conventional entropy. Right? So entropy itself doesn't have a real physical meaning, so we can only call it conventional entropy. And the name conventional entropy means that we're manually set the elemental form of these condensed elements equals to 0. All right. So this part basically is introducing the idea of what is conventional entropy. And we get it to the point to say like, okay, we know that the conventional entropy of any element or compound in internal equilibrium, so this one is a term that's needed, meaning like this compound can't have like non-equilibrium parts, right? You can't have a crystal that one part is more stable than the other, so you have internal reactions going on. Nevertheless, so basically that's telling you any element or compound in internal equilibrium will have zero conventional entropy when temperature approaches zero. So far, so good? So this is the introduction of the term conventional entropy. Next up, we want to see what do we have in hand right now. So first of all, this is one we just did. We know that the conventional entropy of any element or substance equals to zero when temperature approaches zero. So we have a starting point. We also know how to calculate the entropy change at constant pressure, right? So now we have a way to say calculate standard conventional entropy of a substance at a certain temperature in standard state. Right, so remember this is our initial point. And here is calculating my delta S. And we'll see one general example together, and then we'll see a real example to see what scientists are doing in order to get our appendix table data. Let's start it from this example here. So what does it mean here? So we have, say, what we want to do is to calculate the conventional entropy of H2O liquid at temperature final, which is higher than temperature melting and not vaporization, and 1 atm. It may not be standard. We'll just say like, hey, let's keep the pressure at constant. All right, so how do we do it? Again, we're talking about a multi-step processes, so we need to treat each fragment separately and using whatever equations we have in hand. First of all, we started from the H2O solid at 0K. So that's our initial state, right? So in our initial state, what we have is, well, starting from our S naught equals to 0. Right, so when temperature approaches 0K, my initial point is 0. Then we have several steps. If we focus on our first step, which is step A, what's the nature of this step? Now, keeping the pressure constant, we have an isobaric temperature increase from 0K to T melting, where that T melting is the normal melting point of water. Right, so what do we have? So in our previous case, we have delta S for this isobaric temperature change. Remember in our review, let me just put these two equations on the board here for you. Okay, that's my first equation. Right, so my delta S equals to integral of, if I'm looking at delta Sn, Cpn over T dt. Right, so that's our first equation we want to use. And let me just write out my second equation. That's an isothermal or phase change. And that one is delta S equals to the delta H of phase change over temperature of phase change. Right, so these two are the equations we know before. So rewriting that down here, the first step is from 0 to T melting. And we're looking at the CPM as a function of T for H2O solid over temperature dt. So far, so good. There's no news here. But one thing we want to keep in mind is this 0 Kelvin here. So the reason we want to treat the low temperature range is like two things. The first thing is like my 0 Kelvin is not approachable. Meaning like we human beings can't really lower the temperature of an object to absolute 0. We can try to get close, but we can't really get 0 K. And as a result, the CPM naught is not measured when the temperature is smaller than 15 Kelvin. So one of the approximation we used to model this one is to say, like, from statistical mechanics, people can model to say like the CPM at low temperature, or sometimes we also write it as CPM at 15 Kelvin. That's roughly equals to a constant times temperature cube. Or the other way to put it is for this one, we can write our 0 to 15 Kelvin equal to AT cube to T dt, and that equals to 0 to 15 Kelvin AT squared dt, and solve that integral. You can have this one, AT cube to 3 between 0 to 15 Kelvin. Right, and in here, my AT3 is effectively equal to my CP naught M 15 Kelvin divided by 3 and minus 0. So it's just this one. So that's one approximation we want to keep in mind when we're dealing with low temperature, 0 to 15 K. But once we have 0 to 15 K, and then from 15 K to T melting, we can simply using this equation here, or the integral here, to solve for the delta S of the process. And what about the rest of the cases? Now, after A, we get to a point that we have H2O solid, now at melting point. The next one we have, process B. This one is the phase change. Right, or reversible phase change at melting point. And that we can use this equation to calculate. Right. And what about the last one? This process C, what's the nature of process C? We start from H2O liquid at melting point. We end up at H2O liquid at final temperature. Right, so the delta SC is the same expression as my delta SA, which is from my T melting to T final, and then you have the CPM naught, but now for H2O liquid, divided by temperature dt. And adding all three together, we end up having our final conventional entropy of H2O liquid at final temperature and 1 atm. right? So this is like a general demonstration. But again, knowing how this integral looks like is very different in solving a real question. So let's look at what does solving a real question look like. So I'm going to start with this example question here. Let me think. The best way I can do is first go over the problem with you and maybe redraw the picture on the board, and then later on I'll write it on my iPad for you. So reading the problem together, what do we have? We have S2O, and we tell you the normal melting point and boiling point are 197.6 Kelvin and 263.1 Kelvin. So a normal melting point and boiling point tells you my pressure is at 1 atm. It also tells me that the heat of fusion and vaporization, we have the numbers here, and also gives you, these are the heat of fusion at normal melting and boiling point. Gives you that the CPM at 1 atm is graphed. So note that here, instead of giving you an equation for CPM, we have a diagram plotting CPM as a function for ln T. This is a little bit peculiar. Well, we also give you what CPM is at 15 K and tells you what's the difference between the ideal gas and real gas. So let me just redraw the picture for you on the board here. So what do we have here? On the y-axis, that is our CPM. That's our isobaric molar heat capacity. That is in Kelvin, calorie per mole per Kelvin. And on the y-axis, that's our y-axis. On the x-axis, we have ln T. We write like T over K just to make sure inside the logarithm, there's no unit. But why are we plotting CPM over ln T? So this is a simple mathematical expression. So in here, remember, we want to have a way to solve for delta S, to solve this integral, which is CPM over T dt, right? One of the things we know in calculus is d ln T over dt, and that's something you can solve using calculus, and that equals to 1 over T. So what that means is if we write that expression, we have CPM over T dt. So this term, 1 over T times dt equals to d ln T. So this effectively equals to CPM d ln T. Or the other way to put it is by estimating the area below the curve, we have a way to estimate what this integral is. We'll see how to use it. So first of all, let me just reproduce the data for you. So here, on the x-axis, we have the log of the natural log of temperature. So I'll start somewhere here. So that's when T equals to 15 K. It's a little bit too small. And note this one is the log of K. And on the left-hand side, the problem is giving us the CPM at 15 K is 0.83. And then we have our melting point. That's our normal melting point to be 197.6 Kelvin. And my normal boiling point is 263.1 Kelvin. And what we want is at 298. Right, so we have several temperatures that we care about. This one is melting point, this one is boiling point, and this one is our T final. Right. And I'm just going to roughly reproduce the data in what it looks like. And then who one has? This one goes down. and somewhere here. Right. In here we have solid, liquid, and this one is gas phase. So how many different steps do we have here? If we start from the very beginning, that's when my T approaches 0K. That's my starting point, right? Or my state 1. So I'm just going to move on from here since we already have the result plotted on the board. I'm going to start writing it here. So we're going to have our initial state to say temperature approaches 0K. And this one is our solid H2O. So what do we know? We know that not at 0K, the conventional entropy at 0K equals to 0. Right, so that's our starting point. And this is our here. That's my state 1. So from state 1 to state 2, we want to isobarically raise my temperature to 15 Kelvin. It's still solid. So how do we calculate that delta S for the process? So my delta S molar for 1 to 2, that equals to the one we just derived before, which is this one. Right, we're estimating the CPM using this equation, H3rd, and we find out, okay, so the conventional entropy change between 0K to 15K is roughly the CPM naught at 15K divided by 3. Or in here, where am I? We can write this one to be CPM naught at 15K divided by 3. And do we know that? We have our CP naught at 15K to be equal to 0.83. So this is our 0.2. Right, we're moving from 0K to 15K. What about our state 3? So my state 3 is starting from 15K. We're heating it up into a point we're ready for the melting to take place. So this is where my state 3. Right, so state 3 is my T3 equals to T melting, and that is 197.6 Kelvin. It's still solid, the melting hasn't taken place. It's only a temperature increase. So what we have is delta S, the molar conventional entropy change between 2 to 3 equals to this integral of 15 Kelvin to 197.6 Kelvin Cp naught m temperature dt. And we did our derivation to show like this integral is the same as the Cp d ln T or the area below the curve. Right, so that's in calculus, right? So here, that's it. That's the function we are interested in, and that's d ln T. Taking the integration of this function is effectively finding the area below the curve. Now, this area below the curve, it's pretty much just like a triangle. And that gives you my delta Sm from point 2 to 3. Right. And in here, just keep in mind, for this calculation, we're estimating it into 1/2 bottom times the top. So the bottom one is the line P3 over 2 times the height which is the CPM at 0.3 minus CPM at 0.2. And these are the two numbers you can approximate if we look at this diagram here, right? So you can approximate this one, and you can read it approximately like this one is about like 17. This one is like 0.83, that's given. So we can estimate what that number is. All right, so now we're at stage 3. What's the next step? Next step, we have the phase change from stage 3 to stage 4. So my stage 4 here, between 3 to 4, that's a isothermal, it's reversible phase change at the same pressure and same temperature. So my state 4, we have T4 still equals to T melting. So note that this is a straight line. We're still at the melting point. But now we have liquid. Right, so between 3 and 4, which equation should we use? So that's this one, right? And in the question, it's giving us the enthalpy of the heat of fusion and vaporization to be a certain number. So we can read the question and find out what the delta H for melting. Or we can write this one as delta Sm between 3 to 4 equals to delta H melting over T melting. So both of them are numbers given in the question. Now we're at 0.4. What about 0.4 to 0.5? So between state 4 to state 5, we have T5 to be different. Now T5 is at our boiling point or vaporization point. It's still in liquid. So how do we calculate the delta S between my 4 to 5? It's isobaric change of temperature. So naturally, we find the area below here to give us delta S of my 4 to 5. This one, you can calculate it however you like. That's like a trapezoid. So if your that's basic geometry. You can also treat it as a triangle plus a little rectangle. And this one is the same, the area below the curve. And if you look at it, that's going to be delta Sm 4 to 5. That equals to 1/2 ln 263.1, that's the final temperature, over initial temperature, and times 21 plus 19. And that 21 plus 19 comes from, like, if I read it, this one. This is about 21. And if I read it here, this is about 19. It's an estimate. So if I ask this question, you give me like 20.5 and 19.5, it's also fine, right? Just as long as you're using the area below the curve. Okay, so now we're at state 5. Our SO2 is now a liquid at boiling point at 5. Now, the next one to our state 6 is vaporization to become a real gas. So we have my T6. Again, it's still at boiling point. Now it is a real gas. And keep in mind, it's normal boiling point, so my pressure equals to 1 atm. And the way to calculate my 5 to 6 is, again, just delta H of vaporization divided by temperature of vaporization. Yes?
Wait, so is it, you're still at boiling points during state 6?
Oh, yeah, this one should be boiling point. Yeah. Okay, now we're at 6. One more step to raise the temperature to 298, which is the temperature we want. State 7, we have T7 equals to T final equals to 298 Kelvin. We still have it to be a real gas. P equals to 1 atm. Right, so the area here, it's a rectangle, so you can estimate it. No, then we have our 0.7. But we're not finished yet. So the key point here is thinking about what the question is asking. It's asking for the standard conventional molar entropy of my S2O gas at 298 Kelvin. All right, but what do we have here? We have the real gas at 298 Kelvin at 1 atm. So I have 2 more steps to take. First of all, we need to translate my real gas into ideal gas. And then using what we know about ideal gas to have a isothermal pressure change. All right, so these are the 2 topics we discussed before. So what does that look like? So from state 7 to state 8, we want to first address the difference between real gas into ideal gas. So my T8, equals to T final. The temperature remains the same. And I want it to be a ideal gas. And pressure remains the same. So this one, if we read the question, it's giving me my ideal gas and my real gas difference is 0.007 calorie per mole per Kelvin. So just subtract that number to translate our real gas into an ideal gas. Right, or the other way is the SM ideal equals to 0.07 plus SM real. And finally, for our final change, we want to change my T final ideal gas. And we want to translate our pressure into 1 bar. All right, so what do we have? We have the isothermal pressure change of an ideal gas. So this goes back to our original discussion when we're talking about change of entropy for ideal gases. So if you forgot where this equation comes from, I recommend you go back and review our lecture note in the previous section. So in here, we have delta S equals to the integral of R over V dV. That's R ln V9 over V8, or V final over V initial. Or you can rewrite it as R ln P8 over P9. All right. So what is the actual conventional entropy, or the standard conventional entropy of my S2O gas? That's a sum of everything we derived together. Right, so the take-home message here is this is one of those really, really comprehensive problem. This is gonna take you at least 20 minutes if we show it on the discussion worksheet, right? So the key point here is, first of all, to read the axis and find out the way we estimate this area is the same as solving this integral here. That's one piece of information. Second piece of information, be very careful with the state of every step, right? So the last two steps is very easy to miss, right? When we're doing the experiment, we're having the real gas, but the standard state of a gas is ideal gas. You want to translate real gas and ideal gases. Once we have the ideal gas, we can easily use the equation we derived before to solve for the pressure change. The other piece of information is when calculating the standard conventional entropy. After all, we're using this equation here. We're trying to solve this integral. There are two different ways we can solve it, right? So one, we can give you what CPM is. It can be an equation. It can also be something like a diagram. So learn how to read these diagrams and solve questions. This is the first time we actually start from an experimentally measured diagram and try to solve for something. So in my last year's midterm exam, I think I have a practice problem on this conventional entropy. If not, I'll also post some practice problem for these conventional entropy for you. But nevertheless, I'm running out of time. I'll host my office hour tomorrow, so please stop by if you have any questions, and I'll see you on Wednesday.